A few logistics before we get started. Everyone will be kept on mute for the entirety of the talk, but you can ask questions throughout the webinar by either using the question feature on the GoToWebinar GUI or ask your question on Twitter using the hashtag NWA WebWed. I will then read the questions at the end of the presentation. And for this presentation, Roger will also have a question for the audience in the middle of the talk, in which you will be able to answer again via the chat function or the questions GUI on GoToWebinar. And we will let you know when that slide pops up so that you can answer answer the question at that time. So you can follow along with the presentation on Twitter using that same hashtag NWAWebWeb, or you can also follow the NWA account at NWAS. This webinar is being recorded as well for later viewing. All right, so I am pleased to introduce our speaker today, Roger Edwards. Roger is currently a lead forecaster for the operations branch at the Storm Prediction Center. His professional career first began at the National Hurricane Center, where he worked as a tropical analysis and forecaster. Hopefully I'm saying that correctly. Roger then joined the ranks of the Severe Local Storms Unit within the National Severe Storms Forecast Center, which was the predecessor to SPC in the early 90s. And stayed on with the SPC when it relocated to Norman, Oklahoma in 1997. He has been with the SPC now for 25 years. Roger also serves as the focal point for the SPC Tropical Program and has contributed to multiple peer-reviewed papers and invited presentations on supercell thunderstorm analysis, tornadoes, tropical cyclone tornadoes, and more. So one more thing before I hand it off to Roger. His presentation contains a really cool animation near the end of the talk, which does not display well here in GoToWebinar. So similar to last month's webinar, I've uploaded the slide with that animation, which you can access via the link that I just shared in the GoToWebinar chat GUI. So go ahead and download that presentation with the one slide in it, and so you can follow along and watch the loop in high resolution. Okay, now to the presentation. Take it away, Roger.
Thanks very much, Becca, and thanks to NWA for being able to set up these monthly or seminars. And it's a pleasure to be here. It's an honor to do this. That's me at the right. Unfortunately, that was before I had surgery to correct this problem I had with monitors growing out of the back of my head. That's since been fixed. So this is a talk on tropical cyclone tornadoes, and it's a specialty of mine. It's bridging the gap between hurricanes and severe storms. And so I'll see if I can move this forward here and see if this will do the trick. There we go. I just had to figure out which button. So as an overview of facts regarding tropical tornadoes, I'll cover all of these through the remainder of the talk, and I put this up here so you can look back at it for reference as in list form. One important thing to remember about this is that tropical cyclone tornadoes can occur in a wide variety of environments, at a wide variety of distances from the center of the storm, and in a wide variety of distances inland. But they're most common in the area of less than 50 knot winds out on the periphery of the circulation and away from some of the more dangerous areas of gradient wind in the center, as well as storm surge. And so the hazard with the tropical cyclones can extend far out from center when you're talking about tornadoes. Moving forward, where do they occur? Well, this is taken from a climatology that I've put together on tropical cyclone tornadoes, and I'm going to use the acronym TC for short to save some time for tropical cyclones. Hurricanes, tropical storms, and tropical depressions, as well as remnant lows that are still tropical in character and have a closed circulation. This is the tornadoes that have occurred with all those since 1995. Why 95? We start with the era of the WSR-88D, the National Doppler Radar deployment, so that we have a common, constant basis for accumulating tornado records in the modern warning verification era. So since then, we've had over 1,400 TC tornado events, and this is their distribution. The red dots are the weak tornadoes, EF0 to 1. The blue dots are the EF2 to EF3, or the strong tornadoes. We've had no EF4s or 5s in the 88D era, although there are 2 EF4s on record in history, one of which moved on shore after midnight in Galveston in Carla in 1961. So they can happen. It's very rare. Distribution by year. This graph goes from that same timeline from 95 all the way to 2017. And so you can see it's highly variable. The most active tropical seasons like 2004 and 5 have also been the most active tropical tornado seasons. That period since then, when there was a lack of major hurricanes making landfall on the U.S. coast, also has corresponded to a general lack of tropical cyclone tornadoes, except for 2008, when Ike contributed quite a few to that total. But in 2017, we ramped it back up again, thanks to Harvey and Nay and Irma, very prolific tornado producers. This is a chart of the tornadoes, the tropical cyclone was classified at the time of the tornado. So in this case, in red, you see hurricane, in gold, tropical storm, in green, tropical depression, and in a remnant low or post-tropical in gray. You see most tropical cyclone tornadoes do not occur with hurricanes. They occur with tropical storms, depressions, and remnant lows. And this is the classifications are taken from the HURDAT data set that's maintained by the National Hurricane Center. Moving on to, again, comparing the 88D era to what happened before the 88D era, I had to look at another data set by Schultz and Cecil and do some comparisons. And in this case, you can see that comparing the pre-88D era, 1950 to 94 at left, to the 88D era at right, far greater percentage of the tornadoes are EF0 in nature, were weaker. And we can attribute that to a lot of factors: emphasis on warning verification, storm surveys, damage reports, media, spotters, maybe even a few chasers. But the proportion of weak tornadoes has increased quite a bit in the record, not in the real atmosphere necessarily, since the radars were installed. That's what we call a secular influence, or a non-meteorological influence on the record. And we see that in all forms of data: wind, hail. This is how it's manifest in the TC tornado data. Here's another way to look at it, to compare before and after the 88Ds were installed. Again, using 1995 as a breakpoint year. In 23 years since then, we've had over 1,400 tornadoes from TCs. In the 45 years before that, we have just a little over half that many on the record. Again, far more active reporting and surveying and warning verification efforts contribute to that. Like Letterman, we can do a top 10 list. Here is a top 10 list as far as we know. These numbers are subject to change as new information comes in terms of the most active TCs that were tornadic. Ivan is the king with 118 in a 3-day period in 2004. Orton formally surveyed the Hurricane Beulah tornado swarm in 1967 and came up with 115, and that's a fairly well documented event. But they're close enough to each other, the margin of error may essentially renders them tied for the top TC tornado producer. And you can see the rest down the list. Harvey was a very active storm with 52 over a 7-day period, which was by itself a record. I'll show more on that later. The most active TC tornado producer, of course, as we have seen, was Hurricane Ivan. Here is a map of the tornado production with different colors for the 3 days that it did so. The first day was the landfall phase on the 15th. And this was a swarm of tornadoes that occurred near the Florida Panhandle coast, southeast Alabama, southwest Georgia, as Ivan was approaching the coast and then making landfall. Nighttime happened, instability weakened. Then again, the next day, 16 at 1800 UTC, that's the center position colored in purple, and the tornadoes with respect to that off to the northeast that day, near the Savannah River and up toward the highlands of northeast Georgia and northwest South Carolina. And then the third day was very prolific. That was our first and still only moderate risk for tropical tornadoes. It verified with a very dense swarm of tornadoes in northern Virginia, Maryland, West Virginia, Pennsylvania, and northern North Carolina. Very prolific producer, a very exceptional event over a 3-day period. So we'll shift gears a bit. This is a polar graph, and it's set to center on the center of the circulation of Ivan throughout the whole 3-day period. So you're following along with Ivan there at the center. You're following along with its center of circulation. And so its tornadoes, the red dots, are distributed north through east through southeast of the center in a pretty tight sector, about 200 to 600 kilometers out. Most of them 200 to 500 kilometers out. This actually fits climatology of tropical tornadoes very well in terms of where they are with respect to the center of circulation. Another active system that we remember well for other reasons was Harvey. Last year, almost a year ago, I said 11 months ago, produced what, at least for now, is known as 52 tornadoes, but in a 7-day span, which is a record duration. We don't have a record of any other tropical cyclone producing tornadoes for a week. That's attributable to the slow motion. It moved back out over water for a brief span on the Texas coast and then back in again. The Houston area was especially badly affected, not just because of the numbers, but because of the overlay of hazards. There were tornado warnings that involved people being told to take shelter on the lowest level or in underground, but it was not possible because of flooding. There were people who saw tornadoes from the roof of their homes because they were trying to get away from the floods. So it was a very awkward situation, a dangerous situation potentially. Fortunately, those tornadoes did not injure or kill anyone in southeast Texas. So getting back to climatology, here's a distribution of tropical tornadoes by the EF scale rating. And this is not necessarily tornado intensity. We don't want to conflate rating with intensity because damage does not necessarily sample tornado intensity all that well, as those of us on the Great Plains know. But to the extent that it does, it's apparent that tropical cyclones tend to produce weak tornadoes, EF0 to EF1. They also tend to be short-lived, small in size, and but that doesn't mean that if you get hit by one, it's any less of a hazard. Very uncommon to have an EF3 or stronger tornado damage from a tropical cyclone. Now, what about the climatology of day and night? Well, in some ways it is like night and day. Tornadoes tend to occur from tropical cyclones preferentially during the daylight hours, especially midday into early evening. This is Z time or UTC time on the bottom of the graph, and I've got 3-hour bins here from that whole record from 95 to 2017. So I've got day colored in yellow and night colored in blue based on local time in the eastern and central time zones in the Gulf and Atlantic coast as a loose approximation. So tornadoes are occurring during the day. That's because of the subtle warming that can occur in that deep, moist environment. That subtle warming can change the instability greatly to where only a degree or two of change throughout the entire profile of warming can change the CAPE from none to enough to support a supercell very quickly. Here's the distribution of tornadoes once again on one of those polar plots like we saw, except I'm doing it 2 ways here to show you the difference between north relative on the left and storm motion relative on the right with the arrow. You notice the motion relative following along with the motion of the cyclone is a little messier, and the events are flung around the circulation a little bit more. The north relative distribution is tighter. That's in part related to the ambient wind and shear vectors distributing the favorable low-level shear for tornadoes preferentially on the east and northeast sides of the system in the northern hemisphere. And also partly due to the motion of some storms toward the south. If they lurch toward the southwest, that doesn't change the physics of the atmosphere around the storm. It just the storm motion changed within that. And so that threw some of the tornadoes back into what you might call the wrong quadrants. Now, I sorted those two scenarios out where storms that had a southward translation component, in other words, the center of the storm usually turns southwest or stalled and moved slowly south, like Harvey did when it moved off the Texas coast. And when storms do that, they tend to have tornadoes on the left relative sector when you're talking about the motion of the storm. So that's why it gets messy like that. So we tend to climatologically prefer to look at tornadoes with respect to true north and not with respect to storm motion. So how does this apply to forecasting concepts? Well, here's the slide that Becca talked about where we have an audience participation question. Before we get to the question, what I'll do is explain these four polar plots. Upper left is all the tropical cyclones in the data set and the distribution of those. Upper right is H, means hurricanes. So you can see that hurricanes tend to distribute tornadoes northwest through east, southeast to center, very, very few to the southeast or south. Tropical storms, the distribution starts to skew toward the east and southeast. And for depressions and remnant lows and unclassified systems, northeast or southeast, with not that many to the north. So the question is, why do hurricanes in particular not have too many tornadoes southeast through south of center in our record?
And you
so
can, again, go ahead and answer this question either in the chat GUI or on the questions GUI, and I will go ahead and relay that to Roger. We'll give you about 30 seconds or so to answer this question. No pressure. Ha, ha, ha. It's a good one.
I hope we're getting a few answers.
One so far. Okay, there's, oh, wait. All right, we have a couple answers. So one is either, one says greater subsidence. The next is EH is maximized there as the circulation weakens. One person was wondering, is it about the hurricane structure? Previous destruction from the eye wall makes tornado confirmation difficult.
That last answer is a really clever one, by the way. That could play a role in some of the lack of distribution of tornadoes in close to the center, but it's not the right answer, unfortunately.
Let's see. Yes, we definitely appreciate your answer, Jennifer. All right, so we got a couple other answers. Prior to landfall, the tornadoes in the southeast are offshore and missing in the database. And then the southeast sector moves onshore as the TC weakens. So there's your answers.
Yes, somebody got it. This is the first time that I've given anything resembling this talk and someone got it. That is exactly what's going on. It's brutally simple. The southeast and south parts of hurricanes, mature hurricanes, tend to be offshore. except in a few cases in Florida, especially where the peninsula sticks out the way it does. And so that's why we don't have records of tornadoes and hurricanes south of about due east, because of the orientation of the Atlantic and Gulf Coast. Tornadoes may be occurring offshore, but we just don't sample them. And so that was, whoever answered that gets a virtual gold star and a virtual can of Dr. Pepper, because that's an excellent answer.
Yes.
Thank you. Well, moving on, this graph is colored by the tropical cyclone tornadoes. And so in the fainter black and white dotted lines represent tornado distribution nationwide. This is from a paper that I did with Brian Smith and Andy Dean and Rich back in 2012. It was part 3 of a large study of convective modes in tornado events nationwide. And so we broke it down by convective mode for tropical cyclones as well. And those are the colored lines: discrete storms, discrete supercells, clusters of convection, or lines. In other words, fairly solid lines, and spiral bands would be included in that as well, where there's not a noticeable gap in that, or an embedded supercell. Some tropical cyclone tornadoes are not produced by supercells, at least by apparent supercells. We get tornado reports from amorphous blobs or from just totally nondescript reflectivity signatures sometimes, but those tend to be uncommon and weak. In September, the tropical tornadoes dominate the U.S. tornado database when compared to all other causes. So you can see those peaks rise up above the dotted black lines. And they're also fairly common in July and August as well. So that was a really interesting finding in our study, is the dominance of the tropical tornadoes in September. Now we're going to shift to forecast concepts and gradient-based thinking. It's the same as with mid-latitude storms. The ingredients we look at are pretty simple: moisture, instability, some source for lift, and vertical shear. The problem is they're distributed different in tropical cyclones, and it can be a lot more subtle in terms of especially the instability and the lift. TCs tend to have no problem with moisture. They tend to have strong low-level vertical shear, big hodographs, often much bigger than mid-latitude storms. But the problem is diagnosing and forecasting the instability, because it's so moist, so cloudy, the lapse rates are weak. We really look for cues in terms of what can destabilize the atmosphere. And again, like I said before, it only takes a degree or 2 of heating to introduce CAPE to environments like that. And sources for lift can be either strong or subtle: spiral bands, embedded boundaries, and by boundaries I mean fronts that the storm can interact with. We'll show examples of that, or kinematic boundaries like confluence lines. But this is one reason among many that we still do frequent hand analysis of tropical environments and also even in mid-latitudes, is to tease out these subtleties that don't tend to be readily apparent in objective analysis and in even high-resolution short-fuse models. Speaking of objective analysis, you may wonder, what about our objective analyses that we have on our site, such as the SPC, surface OA, or mesoscale analysis site? We actually tested those for some environments in 2003 to 2011, and what we found was that between weak and strong TC tornadoes, there's not that much difference. You would expect high moisture content, weak lapse rates, low CAPE compared to mid-latitude. And of course, more compressed distributions for some of these parameters. The thing is also that the model on which these are based, and for that study it was the RUC, was not a tropical model. It was not designed for that environment where you have extremely strong wind gradients and pressure gradients in a nearly barotropic setting. And so the RUC was, as you got closer to the center of the storm, tended to produce some really funny looking stuff. We don't have as much of a sample size with the rapid refresh model to say, but once we do, I'd like to test that as well. It's important to remember, though, that indices and parameters, they're not forecast parameters. They're diagnostic, and they can change greatly from one hour to the next, especially in this environment. Again, you can heat by just a degree or two and go from no CAPE and no SIG-TOR parameter to, in an environment of large photographs, enough CAPE and a lot of shear and a lot of SIG-TOR. So you have to understand the ingredients of the index. Don't just blindly use these indices. Understand the influences and biases of the model, and understand that they're not well tested for these kind of environments. So there's really no substitute for that kind of understanding involved. Here is an example of a sounding in the environment of a tropical cyclone tornado. This was a big typhoon that moved onshore in southern China in 2015. And so you can see really large low-level photographs for a northwestward moving storm, which is represented by this dot, a northwestward moving supercell. So that's large storm relative helicity, 0 to 1 SRH over 250, effective SRH over 300. These are very favorable parameters. They're typical of the tropical cyclone tornado environment, which is why I picked this sounding, even though it's on the other side of the world. Very large low-level flow. You can see that we're on the outer side of the circulation, as I'll illustrate. The surface winds are fairly weak, but they strengthen rapidly with height. And that's the thing with tropical cyclones, is that tornadoes tend to occur in areas of strong shear, not necessarily strong flow. And that's more on the outer part of the cyclone. And you can look at these other parameters or look back at the presentation to see some of the other parameters that are analyzed here as well. But one other thing to notice is that the red is temperature, green is dew point. And as we go up with height, we'll notice this is a very skinny, so to speak, CAPE profile, but also very deep. These are deep updrafts. They're just not terribly strong, except where they're supercellular, which strengthens them. And this is fairly typical of TC environments as well. Weak but sufficient instability. You don't have to have top flight parameters across the board to get tornadoes, and they didn't. Here's that same system moving ashore in southern China. The center of circulation at the time of the satellite image is here, right in this area. It's 14 local standard time, or about 2 p.m. in the afternoon. The tornado is east-northeast of center from this cell, right about where we would expect climatologically on radar. Here is a nearly matching radar image from one of the Chinese radars. You can see that the eye of the hurricane here. The tornado is from a band-embedded supercell out here to the east-northeast of center. And there were multiple rain bands and multiple tornadoes being produced. And this was an EF3 as rated by the Chinese Meteorological Agency. And the reference on that is BIAT-L 2017 in BAMS, in case anyone wants to look at that. So we analyze for subtleties in the environment, and among those are baroclinic boundaries, pre-existing fronts or fronts that storms interact with. So here's what we call a shear limiting case. In other words, the CAPE is good enough for supercells on all sides, on both sides of this baroclinic zone here. But the shear was maximized where this flow is back from the east and east-northeast on the north side. Supercells formed in Earl to the south of the warm front, crossed the warm front, and then started producing tornadoes. The buoyancy limiting case, Floyd was a great example, where the air mass along this residual damming front in eastern North Carolina was cold on the west side, prohibitively cold for the survival of supercells. Supercells formed over the Atlantic, moved onshore. I recall numerous mesocyclones being visible from Morehead City's radar at the time, and they produced tornadoes where they were able to get any records of them. They were probably producing over the sound and offshore too. They hit that front and the production just shut off. Here is a case where we have what we call a buoyancy shear overlap. The favorable buoyancy was on this side of the boundary, which is represented by these changing positions with UTC time northward ahead of Charlie. The favorable stronger shear was on the north side, but it was a little too rain cooled and stable. So we have a narrow zone of overlap that was favorable for tornado production. It also happened to be along the northeastward path of the TC. most of the tornadoes occurred right in that slot of buoyancy shear overlap. However, one fairly long track tornado occurred south of Lake Okeechobee. All this underscores the need for strong attention to diagnostics, especially hand analysis, but all kinds of analysis: satellite, radar, soundings, special soundings, bad wind profiles, every tool you can to diagnose these subtle environments. So we have another case here. This is a hurricane, Katrina specifically, offshore from Louisiana, that was forecast to look like these two panels by two different resolutions of a wharf with an ARW core, high resolution convection allowing model. And you can see in both of these panels what appear to be supercells in the favorable sector, spiral bands where you would expect strong lift, in the east and northeast parts of the storm where you'd expect favorable shear and instability. And in the higher resolution model, it looks like it's just infested with supercells. The hurricane is liberally sprinkled with model supercells. Very precise forecast, but how accurate was it? Well, based on the aircraft, the NOAA P3 that was airborne, at about that time, to verify those panels that left, not very accurate at all. The storm had, at the time, very few supercells in it, although it did produce quite a lot of tornadoes inland later, a day or so later. But this goes to show that you can't just genuflect and bow down to the convection allowing models, because they may be wrong. And as we've seen with mid-latitude NCSs this summer, they often are wrong. And they're most certainly not designed to handle the intense gradients and baroclinic structures that tropical cyclones often present. So here's that slide that Becca was talking about, that hopefully you've been able to download the animation for it here. Or no, this is, I'm sorry, I'll back up. That's a later slide. This is a slide that shows dual polarization output, specifically the rho HV, or the cross correlation coefficient at the panel at lower right, for a tropical cyclone in 2011 in North Carolina, not far from Swancourt. If you look at the reflectivity presentation in the upper left, it just looks like a big nondescript blob. Upper right, there's a velocity signature there. That would definitely raise suspicions. Something's going on. Spectrum width is at lower left. There's definitely something going on there. Stands out very, very well. And it stands out best at lower right here in the rho HV, or correlation coefficient fields. And that's because there is a tornado there. It's lofting debris. It's probably mostly vegetative debris in the form of marsh grass and pine needles and substances like that, given where it's at. Nonetheless, that stands out dramatically in terms of the correlation coefficient compared to a fairly uniform distribution of warm cloud raindrops around it. And we found, Joey Pica and I in our study, that these tornadic debris signatures in tropical cyclones tend to stand out better in this environment than in most others. They can be really, really vivid. So that's one tool that we can use to diagnose the presence of tornadoes, and hopefully alert to downstream for the potential for other tornadoes. Here's a cross section of that, looking from west-southwest at the left to east-northeast at the right. You can see that there actually is, and this is a westward moving tornado, you can see there's a tilt of debris with height off toward the northwest in a plume, or off toward the southwest in a plume, like you normally expect to see with these things. So these show up very, very well. A dual pol is a very promising tool for diagnosing tornadoes and TCs. Here is a slide with the animation, and if it doesn't work for you on screen, hopefully you've downloaded it as well. At the top, this is the phased array radar from Norman, looking at a 60-degree sector southwest of the radar. So the radar is actually up here at the upper right of the view, the phased array radar from Norman. This half-degree elevation, the sampling interval is 43 seconds. And at the bottom two panels, that's WSR 88D, Oklahoma City, The sampling interval at the time, and this was before sales, was 4.1 minutes. But even with sales, phased array radar promises much better sampling than the 88D as it now stands. And in this case, at the upper right, it picks up on a mesocyclone, tornado-warned supercell, and the subtleties within that much better than the 88D does with its coarse resolution and lower sampling interval. So there's another technological promise that we have for the future, and hopefully sometime before I retire, before I die, we'll get phased array radar capability nationwide. So we'll change tunes here a little bit and go to SPC outlooks for these scenarios. And here's an example I was talking about earlier for Ivan. It's the only moderate risk we've issued for a tropical tornado situation. It adjusted northward with time, and it was a good forecast. There are a lot of tornadoes, as I showed earlier, in this part of the storm. We tend to discuss these forecasts on the Hurricane Hotline, which is an internal coordination with the Hurricane Center and WFOs along the coast, as well as regions and headquarters and other entities. DOD as well gets on those. And so we coordinate the messaging of the tornado threat in hurricane advisories, as well as occasionally discuss potential for watches that may be coming up. Here's another example. This is more recent. This is for Harvey. This was a couple of forecasts that I was involved with Mr. Smith for the morning of the 27th of August. And in this case, this was a slight risk that's triggered by a 5% tornado probability. The marginal is triggered by a 2% tornado probability. And this was one of the days in which cluster tornadoes happened around the Houston area, and the threat extended eastward along the Louisiana coast. So this is a fairly typical example of what we might issue since the marginal risk category has actually come into effect. Mesoscale discussions, as we drill the threat down in space and time to a more concentrated threat. Here's an example of a mesoscale discussion that Brian issued northeast of the center of Hurricane Harvey shortly after it made landfall. And it highlights areas where certain parameters are more favorable for tornado production. We issue mesoscale discussions both for the potential for a watch, in which case we'll tell you the probability of a watch issuance, or for updates to existing tornado watches. In this case, it was an update to an existing watch that had already been out. Speaking of watches, here's what they look like. These are probably very familiar to most of the audience. We still have a legacy polygon, but that's not emphasized. It's mostly for aviation use. The watches are really issued and verified by counties and by marine zones that you can see here, and they're more targeted to a situational tornado threat. Tropical tornado watches tend to last longer, especially for very slow moving systems like Harvey. This was, I believe, an 11 or 12-hour long watch, which is long for us, but if the system's not moving much, what's the point in issuing a bunch of smaller watches when one long one will do? They are cleared and extended by the local WFO, and tornado probabilities are offered with each watch. And one thing I want to emphasize is that we don't necessarily issue watches for all tropical cyclones. It's based on the threat. Some TCs don't produce tornadoes or produce very, very few, and as such don't deserve watches. Here's an example of the same watch with the watch probabilities for tornadoes overlaid with the radar image at the time. And so you can see the watch extends inland somewhat into the more rain-stabilized air mass, but not completely. This sector normally would be climatologically favorable, but we didn't put a watch up there because it was too stable, too much rain, not enough cape. And so we didn't extend the watch inland. Tornadoes didn't happen up there. Impact, I mentioned the impact, and it's not just in terms of that extreme example that I talked about with the flooding and folks on the roof. Houston and Harris County, which is in yellow, spent 60 hours in tornado watches in Harvey. We haven't been able to find any other instance where a major city has spent so long in tornado watches continuously. This thing sat down over southeast Texas and wouldn't move. And so the threat did the same. Now I'll slowly move forward here, and so you can see Harris County stays in watch after watch after watch for 60 hours. In parts of their county warning area in Houston, we're in tornado watches for 96 hours, which is unheard of in our history. And so even though tornadoes were a secondary threat by far to the heavy rain and flooding, this is still something that they had to deal with, both at staff at the office who were already exhausted and stretched to the limit, and the public who had the same situation. So I'll go ahead and start to conclude this. Here's a link to our forecasts, our web page to go directly to our forecasts for those who don't know that already, and my email address if you come up with any questions that you don't get to have answered here today, or you want to ask later that you think of. Fire me an email. I'll be glad to answer them. I love talking about tornadoes. I love talking about hurricanes, and so this is good stuff. And then I'll just move forward to one reading assignment I have for folks who are especially interested. I did a formal overview or review article on tropical cyclone tornadoes in 2012. The concepts are still valid, except it doesn't have dual pole radar information in it. And that's on the Electronic Journal of Severe Storms and Meteorology website, ejssm.org. And it's also available on the SPC publication site. You can go to either and find that paper and read pretty much anything you wanted to know about TC tornadoes and then some. So with that, I'll conclude. I'll leave this up here, and thanks for joining in, and I guess I'll answer questions as Becca presents them.
All right, everybody, go ahead and type in your questions into the questions GUI, or in the chat box, or on Twitter using the hashtag NWA WebWed. We have a couple questions. So first and foremost, to follow up to the our audience participation question, we have one here. But if the strongest part of the hurricane or storm is the northeast quadrant, where the largest convection activity and heavy downpours and thunders are concentrated, is not supposed to see the biggest tornado activity in that area?
Don't understand the question. Can you repeat that?
Sure.
One?
If the strongest part of the hurricane or storm is the northeast quadrant, where the largest convection activity and heavy downpours are concentrated, are we not supposed to see the biggest tornado activity in that area as well? Is that better?
Well, the northeastern quadrant tends to have the most tornado activity, not only because it has some of the strongest convection and some of the most common areas of supercell potential, but environmentally speaking, it also has the greatest juxtaposition or overlap of favorable instability of CAPE, as well as favorable environmental shear. And so there's a legitimate physical reason for that tornado distribution. Now, we can get strong and severe convection in the other quadrants of a tropical cyclone as well, but when you overlay instability and shear with favorable convective modes, which are also most common in that part of the cyclone, that's why we have the most tornadoes north through southeast of center in the outer part.
Okay, thank you. Next question. Is there any well, first of all, we have a comment, nice talk, very good talk. And then the question, any solution to the combined flash flood and tor threat messaging?
That's an excellent question, and it's one that absolutely bedeviled the Houston office in real time during Harvey, because they were faced with an unprecedented flood risk, not just flash floods, but standing floods, given how horrendously voluminous that rain event was. And we're still early in the stages of trying to figure out what to do with this. Their MIC Jeff Evans, who's a former SPC lead forecaster, has been leading the charge in terms of trying to get some people together and figure out better ways to message that hazard when the can statement says take shelter underground or in low levels, but the floodwaters prevent that. I don't think there's an easy solution to that problem, but if there is one, I'm confident Jeff and his crew will help to find it.
All right, next question. So we have more tornadoes in tropical, or why do we have more tornadoes in tropical storm and tropical depressions? And then in hurricanes, we have low tornado activity.
That's a good question. Part of the reason we have more tornadoes in tropical storms and tropical depressions and remnant lows is simply because these systems spend more time over land in those stages than we get as hurricanes. So if you were to break it down in terms of storm hours, for example, tropical cyclones and depressions and remnant lows simply exist for longer time over land in the United States than mature hurricanes do. And another part of the reason for that also is, of course, what we showed earlier with that question, where we are getting tornadoes with hurricanes in all likelihood based on radar signatures. We're just not sampling them because that part of the storm is over water at that time for a lot of these hurricanes.
Alrighty, next question. Is there a disproportional impact that dry air intrusion has on the convection in the southeast quadrant?
Yeah, that's a good question about dry air intrusions. Lon Curtis did a great study, I guess nearly 20 years ago now, on the association between dry air intrusions and tornado outbreaks. And it is an associative thing. There's an indirect physical relationship too, in that dry air intrusions tend to carve out slots of relative cloud-free skies in tropical cyclones, and that can help with destabilization. It can help to set up differential heating boundaries, which can be sources of vorticity for supercells to interact with. And it can also set up areas where instability during the daytime builds, and that air can be infected or blown into areas that are cloud covered, but it's still more unstable. And so that can help in terms of those subtle increases in instability that I talked about, that can help a supercell to form and maintain itself to produce tornadoes. So there's several indirect effects of the drying aloft, but it's more of an indirect cascade effect or domino effect than anything direct.
Okay, we have another question here. So how are systems studied for tornadic environments when they become extratropical, like with Sandy? Does the distribution change at all?
Generally, when a system becomes extratropical and is no longer identifiable as a tropical cyclone, no longer a warm core, one of two things is happening. It's actually three things. It's either moved back offshore again, in which case we don't have to worry about it tornado-wise. Another thing is that it's been absorbed into a baroclinic system. The lapse rates are low. Tornadoes can still happen, but are not very common because by that point there's a lot of rain, a lot of stability. You're at farther north latitudes, and so the instability is often not there. And the other thing that can happen is that a tropical cyclone moves inland, weakens to a point where it's not classified anymore, but the low is still warm core, is still identifiable as a closed circulation, and it still has enough shear. Even though the wind speeds are weak, there's enough shear to where the winds above the surface haven't weakened as fast as the winds at the surface. And so the shear is still there, and it can still produce a few tornadoes. And we've seen that on a few occasions as well. And when that happens, it's still a tropical low. It's just not classified anymore because it's too weak. And so I do include those tornadoes in my records as long as there's an identifiable closed circulation.
All right, next is sort of a comment kind of question at the same time. In regards to the less tornadoes analyzing hurricanes, is this due, or could it be due to greater than or equal to EF 0 to 1 damage from the ambient hurricane force winds? So maybe there's some sort of confusion there between what is tornadic damage and hurricane damage.
That's probably a factor, especially as we get closer and closer to the center of the storm, and the gradient flow in the hurricanes gets more and more intense. And that is one that is very difficult to tease out in terms of damage assessment, although one thing that we hope dual pole radar will help us with is those kind of tornadoes that are lofting debris, which the ambient flow of the hurricane doesn't tend to do. And so we can better target damage surveys or places to look for tornadoes. In some cases, we may never know. It's just one of those things. Tornadoes occur in remote areas, swamps, marshes, sand spits, and we just don't know it because of where they are. They're rain wrapped, they're hard to see, nobody's out there spotting them. And another thing with that too is that tornadoes appear to be legitimately fewer in number as we get closer to center, because the central dense overcast reduces instability, and because even though the winds are stronger, the vertical shear is not. The change of winds with height. So there are factors that legitimately physically reduce tornadoes with inward extent, but we're probably undercounting them as well. And which one is dominant, we don't know yet.
Makes sense. All right, this one's kind of long, so bear with me. If you need me to repeat the actual question, I will. All right, the National Weather Service in Puerto Rico, before Hurricane Maria destroyed the radar, detected 3 tornadoes despite the fact that the radar is at a height of about 1,000 feet on a mountain, and therefore it is difficult to visualize the tornadoes or hail activity on the radar. So when we have the radar so high, and it doesn't see what is happening on the surface, what would you recommend doing to be able to better detect tornadoes within the structure of a hurricane?
Well, I'm glad that, excuse me, I'm glad the Puerto Rico example is brought up because I did want to mention that the database does not include tornadoes outside the contiguous 48 states. So it doesn't include any tornadoes that occur in general. This is the whole tornado data set in Hawaii or Alaska, Puerto Rico, Virgin Islands, Guam, other outlying territories. But as for that particular scenario, the radar level is 3,000 feet. Fortunately, Puerto Rico being as small as it is, the beam does not have a chance to get very far above ground by the time it leaves the island, very far above the radar level. And so you're still not going to overshoot most tropical cyclone supercells, even as shallow as they can be, by the time that they're either approaching the coast or they're actually inland over the island. Now, if you're looking further out, such as at the farther parts of the Virgin Islands, that might be a consideration. But compared to the depth of the atmosphere from sea level to the radar is a very small distance. And so I don't think that's very much of an effect in terms of tornado or especially supercell detection. One thing I did want to say as well, I'm glad that question was asked because it brings up the difference between detecting supercells and tornadoes. Because TC tornadoes tend to be small and weak and short-lived, radar usually does not detect those directly, at least not the 88D. We can only infer them through the presence of a strong mesocyclone, or as low as it can look, or the presence of a tornadic debris signature, which tells us there's a high probability of a tornado in that location. So that's sort of a long-winded answer to the question. I didn't mean to make the answer almost as long-winded as the question, but that's okay.
No, that's great. That's a great answer. So this is a question for me. I'm sort of curious as to how you guys at the SPC will incorporate GLM data into the potential for forecasting supercells and potentially tornadic supercells within a TC. Either, I mean, I guess this would be most beneficial over the open oceans. How will that impact your decision making and your forecasting for tropical cyclone tornadoes?
And I can see why you asked that, Becca, since you're a GOES 16 satellite guru.
Yep.
We'll use it very similarly to how we've been using remotely detected lightning data. It'll just be one more tool in the toolbox, basically an affirmation, since we do have other remote lightning data sources that extend far out over the oceans. And I'm glad you asked that question because I didn't get to it in the talk. I didn't want to make it even longer than it was. But tornadic supercells and tropical cyclones, because of the effect that the mesocyclone's vertical pressure gradient force has on strengthening and deepening the updraft, they tend to be, even though they're relatively shallow, they tend to be deeper than other surrounding storms. So often, not always, but often we can infer the presence of a supercell in a tropical cyclone by a trail of lightning that it's producing when no other storms around it are. And that's a long-known effect of tropical tornadic supercells since the 1990s, when lightning detection networks are fairly widely distributed. So the lightning data is very useful, especially as a diagnostic for offshore supercells that the radar may be overshooting. And that's probably the best benefit, both of that and potentially of the GLM data once we get that fully integrated into operations, is we can infer that if there's a trail of lightning occurring with an offshore storm, that's probably a supercell, for one, in the correct environment. And for two, okay, the environment's favorable for a supercell. Even though we don't have very many stations or we don't have enough data to analyze at the surface, we can infer that the environment is favorable and therefore be on the lookout for that environment to shift inland over some period of time into the future. So as part of a bigger toolbox, it can definitely help in terms of mesoscale discussions and watch decision making. More on those time scales than outlooks. Did that answer your question? Have we lost our sound?
Oh, sorry, I had put myself on mute. Ha. Where was I? Oh, I was just saying that we have no more questions. So I just want to thank you, Roger, for an excellent and expansive look on the climatology and forecasting of tropical cyclone tornadoes. Do you have any final thoughts?
Oh, just thanks to you and everybody who organized this talk, and to Alan Seals, who listened in on an early version of this, and to make sure that everything was going okay. And
all right,
I appreciate being here.
Well, it's good to have you. And I'm sure this talk, this information will be very useful for many folks as we head into the tropical season. So again, thanks. And also thank you to the social media committee member, Hannah Strong, who has been live tweeting during this presentation. She's been doing an excellent job, so thank you very much. And that is all we have for now, for this month. We are still on schedule to have the NWA Aviation Committee present at next month's webinar, which will be held, note, it's a little bit later, it'll be held on September 12th. We pushed it back a little bit so that everybody can have a chance to recover from all of the awesomeness that's going to happen at the annual meeting. So keep an eye out for details on that. And please check the NWAS.org website or at NWAS on Twitter for details on the upcoming annual meeting. Thanks again, everybody, and hope to see you all in St. Louis.